Here we come to the example on page 24. So we have an aeroplane turning around a corner, making a turn. And so first of all, part A1, we have to estimate the magnitude of the lifting force. Before doing so, let's try to draw the free body diagram of the aeroplane first. On this aeroplane, we have a lifting force L, which is perpendicular to the wings. And so this lifting force, besides this lifting force, the aeroplane is under the gravitational attraction, which is pointing downwards. So now we are going to resolve L into two components. One is the horizontal component, which is given by L sine 15, and the vertical component L cosine 15, with 15 degrees being the angle between the vertical and L. So now we can write down one equation by considering the vertical balance. We have L cosine 15 pointing upwards and mg pointing downwards. So we can write down L cosine 15 equals mg. This is considering the vertical balance. So put in the numbers. L cosine 15 equals the mass of the aeroplane, 4 times 10 to the power 6. G is 9.81. So solving this, we would have L to be 40624. Okay, let's put it in scientific notation. 4.062 times 10 to the power 7. We are talking about the lifting force, so the unit is Newton. Secondly, we would like to estimate the centripetal force required for the plane to make the turn. In this case, we have the L sine 15, the component, horizontal component of lifting force L, providing the centripetal force. So when you want to know the magnitude of centripetal force, and here it is. So the centripetal force would be given by L sine 15. Now we already know L, so put in the numbers. Times sine 15. And so we have 1.051 times 10 to the power 7. Again, we are talking about force, so the unit is N. Now here, the plane turns with the centripetal force provided by L sine 15 with this magnitude, and now the plane is turning with this centripetal force, and we are asked to find the radius of curvature of the turn. So because F equals ma, we know that the centripetal force would be equals to mv squared over r. Here, we do not use the version mr omega squared because omega is unknown. The angular speed is unknown. However, we have got the linear speed. How do you know the linear speed? How do you know that this is the linear speed? You can look at the unit, kilometer per hour. But as usual, we don't like kilometer per hour. So let's try to change the unit into standard unit first. 300 kmh is equal to 83.33 meter per second. So we change in the standard unit at once. So now we have the centripetal force calculated in part 2. We have the mass, we have the V, and so we can find the R. Let's put in the numbers. Centripetal force is 1.051 times 10 to the power 7. And it would be equals to 1,500 times V squared over r. So solving this, oh sorry, I have put the wrong mass. Let's do it again. Mass is equals to 4.0 4 times 10 to the power 6. V is 83.3 square, and we are going to solve for r. So the radius will be 2643. So because now we are talking about radius, the units will be meter, standard unit. Part B, it said that the speed of plane is unchanged but the tilting angle is smaller. When the tilting angle is smaller, what would be the radius of curvature? When the tilting angle is smaller, let me draw it. Like if the plane is turning with a smaller tilting angle, so the lifting force is closer to the vertical. In that case, if you resolve the lifting force, the horizontal component will be smaller. Okay, so the centripetal force will be smaller. Or you can explain it by the equation tangent theta equals v squared over gr. If theta decrease, the whole tangent theta will decrease. And if left hand side decrease by keeping the v unchanged, the only thing that we can change is that we have to increase the r, so that the denominator becomes larger. So the radius of curvature will increase. The plane has to turn around a corner which has a larger radius.